Hi everyone, and welcome to the National Environmental Science Program Climate Systems Hub webinar, Counting Carbon's Cousin, Australia's Methane Story. My name is Heidi Evans, and I'm a knowledge broker with the Climate Systems Hub. As the knowledge broker for New South Wales, my role sits within the New South Wales Department of Climate Change, Energy, the Environment and Water. So that's New South Wales DQ, not the federal one. Today, we're going to hear Australia's methane story, all that we've learned about that lesser known greenhouse gas. We've got two fantastic speakers, and I think it'll be a really interesting session. But before we begin, I just want to acknowledge the Wongal people of the Eora Nation, the traditional custodians here in Canada Bay in Sydney, where I'm joining you from today. I pay my respects to their elders, past and present, and I'd also like to extend my respects to all First Nations peoples joining us today. The Climate Systems Hub recognises the important role traditional knowledge plays in understanding Australia's climate. We know you're dialing in from across Australia. Please take a moment to think about the traditional owners of the lands where you're joining from. So, a few housekeeping notes before I introduce our first speaker. The webinar is being recorded and the link will be available on the Climate Systems Hub website after. We encourage you to ask questions. This can be done at any time by typing them into the Q&A function at the top of your screen. And also note you can vote for questions that you see appear in the Q&A that you too would like answered. There's also a chat function available also at the top of your screen, but if you can just try and use the Q&A function alone, that would be fantastic. And you would have noticed in your registration form for the webinar, we gave you the opportunity to submit your questions ahead of time. And we've already got a good number of questions ready to go. We'll try to address as many of those as possible after both speakers have presented. But we may not have time to get to them all. So if this is your first Climate Systems Hub webinar, a big welcome to you. These webinars are designed to provide an opportunity for learning and interaction with a broad range of topics and experts. We've had a great range of webinars already this year, and today's will be another. So without any further delay, I'd like to warmly welcome our first speaker, Dr. Pep Cannadell. So Pep is the Chief Research Scientist in CSIRO Environment, Chief Lead Investigator in the Climate Systems Hub, and Executive Director of the Global Carbon Project, a global consortium of scientists under the umbrella of Future Earth and a scientific partner of the World Climate Research Programme. Pep focuses on collaborative and highly integrative research to develop national, continental, and global budgets and trend analyses of the main greenhouse gases, including carbon dioxide, methane, and nitrous oxide. He also studies the size and vulnerability of Earth's carbon sinks and pools, carbon climate feedbacks, and pathways to net zero emissions, including land-based carbon sequestration and negative emissions. So with that, I will hand over to Pep to take us through Australia's methane budget.
Thank you, Heidi. Let me just, very good. Can you see my screen? Wonderful. Thank you so much. Thanks for the opportunity. Thanks, Heidi, for the intro. I'll just go straight into basically letting you know that this research that I'm going to present now, it is a companion piece of research from the Australian carbon budget, carbon CO2, which we already presented in previous webinars. And there's plenty of materials for those who missed out if they want to dive into the research paper, infographics, fact sheets, etc. We've done also the N2O, the nitrous oxide Australian carbon budget, which we'll not be presenting today. And the focus today is the methane. As a way of introduction, I want actually to give you 5 reasons, many reasons, but they're all very important of why methane is so important and why we're talking now more about methane than we used to 10 years ago. The first one is that anthropogenic methane, everything that we have actually added to the atmosphere, is now responsible for 0.5 degree warming global average. That's very significant. And if we look at just how much the carbon dioxide adds is about zero point 0.8 degrees, means that the difference is quite relatively small. Now, that doesn't make CO2 less important. I'll explain this thing why, but nevertheless brings the methane at a very high level of relevance as we try to stabilize the climate. The second thing, and one reason why we have such a huge warming coming from methane, and by the way, methane emissions are a very small fraction compared to the emissions, the total emissions, the volume of emissions from carbon dioxide. But because it's so powerful, they have a global warming potential within the first 20 years after the release, 81 times larger than CO2. And what's important is that we reach what's we call it the peak temperature about 12 years after the release, and then there's this steep decline to of the warming, and in about 40 years, you basically have or 35 years, you have about 95% of the warming, gone already. There's a long tail later on that you need to follow to completely get rid of. But that's in huge contrast to carbon dioxide, we just stay in the atmosphere. We don't give it a lifetime because they have multiple lifetimes, but it can't stay in the atmosphere, or some of it stays in the atmosphere for thousands of years. I'll just laser pointer. Okay, very good. So the next really important, kind of fundamental feature of methane, and that's why it's so important, is that to stop further global warming, methane emissions do not necessarily need to reach net zero. That's quite important, and it's unlike CO2 emissions, which they must be net zero, because whether we're putting few emissions from CO2 or a lot of emissions from CO2, there's always going to be a fraction that's going to stay there for hundreds to thousands of years, as opposed to methane, that if we stabilize and just slightly decline the emissions, we will not be further adding to the warming. We'll just maintain the warming that we already have. In this case, is 0.5. But importantly, emissions have to kind of come down quite dramatically to lower what we call the peak warming. And that's because CO2 cannot do it all to stabilize the climate. So we need every greenhouse gas to make their contribution. And this figure here, it shows hundreds of scenarios from IPCC. And on the left, it shows the reduction, the percentage reduction we need to have for specifically methane for a given peak emissions. Like if we say, let's say well below 2 degrees, here, the second arrow, it would basically show that we have to have about, on average, a 40% decline of emissions from methane. And that's the average. And some scenarios are calling for just about 30% only, and other scenarios, they're calling for as much as 60% emission reductions. So again, we expect a lot, and we need a huge amount of reduction from methane, along with the CO2 net zero, to be able to stabilize the climate. The fourth reason is that, none of the above would be really particularly important if methane were not continue to accumulate in the atmosphere. And that's exactly what has happened for the last 200 years, and concentrations continue to increase. And the last one, it's because we've seen annual growth rates of methane globally, and this is our observations from Tasmania, particularly in 2022, 2023, which is some of the biggest ever in the last 40 years growth rates coming from rapid increase of methane, and kind of showing that there is an increased sensitivity of methane to something that I'll explain now what this something is. And it is not necessarily just our own emissions. So we call it has a very bad temper, and this temper is getting worse. And this is the first fundamental thing that I do want to leave you with this talk. And this is the global methane budget. That's not the Australian one. And what it shows is that here on the left, we have the big anthropogenic emissions, the ones that have initiated this big atmospheric perturbation, which is leading to the climate change. But there are many other components, which we call more on the natural CO2 sinks and sources, like wetlands, some of the wildfires, and then sinks, the destruction of methane or oxidation of methane in the atmosphere, which are part of the natural system. And natural system that now has been uh, perturbed by the changes of these direct emissions from agriculture and fossil fuels by changing the climate and also pollution related to pollution. So some of those big growth rates were not necessarily that all of a sudden we're emitting a lot of methane emissions from livestock, was that something in this natural system was changing very dramatically and very quickly in response to temperature, in response to changes of pollution. And that's the very reason why, when we talk about the global methane budget and what I'm going to show now, the Australian methane budget, we're not only focusing on the anthropogenic emissions, but we're focusing on all sources and sinks, which together determine how much methane accumulates in the atmosphere. Some of it a direct result from us, from our activities, other an indirect result from changing the climates and pollution. So the Australian methane budget, so I'll take a very similar approach with the infographic that I showed before globally with a little more detail just for Australia. And we like to kind of do this at a decadal level. So we kind of avoid the annual changes, but we just have more of a state of the climate, in this case, a state of the methane budget for Australia. So it's 2010, 2019. I'll say a few more things later on, more modern. And what we show is that here, that as we already know, and this comes straight from the National Greenhouse Inventory from the government, that livestock and manure management is the single biggest, most important anthropogenic source, followed by fossil fuels, and then we have a few others, and the more complex ones, which come from the fresh waters, reservoir dams, rivers, streams, which are a little more complex. I do want it that within these and excluding the fresh waters because they're a little more complex, and I'll explain a little more after. What we have in terms of order from the top to the bottom, emission intensity of these sources, we would put enteric fermentation at the very top, with livestock from pasture, beef, cattle beef, accounting for about 64% of all emissions, single most important one, followed by coal mining, managed burning, which I'll show in a second in a different section, solid waste, landfills mostly, oil and gas leaks, and manure. The list continues, but these are the biggest ones. So the next component is what I mentioned before, the natural fluxes. We don't have necessarily all the direct control on these natural fluxes, but now we are indirectly changing them as well. And so that's why we keep track. It's what we call the carbon climate feedbacks. So we have wetlands as the single most important one. It's a very uncertain measure. We don't have a lot of data, so we have to do a lot of modeling and look at a lot of modeling from overseas as well. There's all the fresh water against lakes, rivers, streams. There's also geological seeps, things that have always been there, and they might or might not be changing now because the climate change. We have termites, which is not a small one source, which we think that it's beginning to change a little due to plant productivity changes, due to elevated CO2, and also warming. And then we have soil uptake. There's microbes in the soil that they consume methane, and it's basically it's a sink, and so we're balancing it out against the sources. And then we have a number of mixed fluxes. I mean, fresh water, I already said, was a mixed flux. We have made an attempt to separate it, But then we have wildfires and prescribed fires. We do have the numbers separate as well, but we put them here together just to show, the fire component. And then we have all the work that's going on in the estuary, coastal wetlands, all the coastal ecosystems, and we can make this thing even wider by looking at the immediate coastal zone, which receives a lot of material coming from the inland organic matter sediments, which then some of it can also be decomposed by methanogenesers and just emit to the atmosphere. This figure, it's exactly the same as the previous one. It's just it has much more detail. It's the figure that is in the research paper. So for those who want to dive more into detail, so there's more fine, we just include, the farm dams and the right cultivation. And yes, we separate the manure from the enteric. Of course, enteric dominates, as I mentioned. And it gets more complex as well as we go into the inland waters and the flows into estuaries and coastal wetlands. Again, for a lot of these, we didn't have a lot of data. There's a lot of modeling involved. And our effort here was to really put a comprehensive picture, show the uncertainties based on how well or not well we know all these fluxes so that we can stimulate more research and more observations. At the same time, we realized that it's not all about the anthropogenic or the direct anthropogenic emissions, but there's more to it in managing the global methane budget and the Australian one for this matter. Examples of this complexity comes, as I mentioned, in the freshwater methane emissions, which of course there is a background emissions that have always been there. Rivers, as an example, they always bring organic matter from the land. Of course, we have changed the land uses. We have opened up to farming. We have exposed the soils. More organic and sediments reaches now the fresh waters, and therefore now there's a large component of that methane in fresh waters, which is now due to an indirect impact of our own activities. So we have tried to bring a partition of these anthropogenic versus non-anthropogenic. And of course, many of these fluxes have large uncertainties, as I show here on the lakes example. These lakes are from permanent small lakes to temporary ones, and then separate the reservoirs and rivers and lakes with dams. There's another issue with the natural wetlands. Of course, Australia is a dry continent, but the dark blue and next blue level up means very little or no methane emissions, as you would expect, of course. And the light blue and red shows some of the hot spots. There's a lot of activity in coastal zones. Coastal ecosystems, or what we call the coastal wetlands. And then we do have some areas which might be temporary fill only when there is large increase of rain, or the monsoon, kind of more temporary monsoon, which have lighter components. It's a very large flux, and it's very large, largely uncertain, but it is one key product for us to kind of follow into the future, because wetlands are very sensitive to increased temperature, and with that, increased emissions. There's also a lot of activity in the coastal zone and coastal ecosystems. There's a lot of sediment, as I mentioned before, being brought by the land, the rivers, from the interior, are natural sediment organic matter, are a result of our land activities, land use, and land clearing. And then when it reaches the ocean, we see all these changes and increases in methane, particularly in the top tropical area where monsoon pushes huge volumes of water every year, and with that the sediment and organic matter, which then gets processed, and ultimately methane comes out from that area. We've done a bit of work as well looking at satellites. I won't speak much about it. Peter Reino, coming after me, it will just do a really high resolution application of satellites to detect methane. And then I'll just move into really kind of bringing what's the relative methane emissions contributions to warming from specifically now the anthropogenic component. I'll leave the natural component aside and I'll pick it up later. So what you see here is the jump from 2010 to 2019 from the full decade that we just studied. And we've seen that overall there has been a decline in methane emissions. Again, this comes straight from the National Greenhouse Inventory. We had not reassessed the entire national inventory. This is a humongous piece of work with dozens of people involved and over the years, hundreds of millions of dollars invested. Peter, after me, will discuss, new methodologies to look at more specific, specific sources and, showing that perhaps some of the estimates they need to be significantly improved from what it's being now, but just now showing only what's already in the National Greenhouse Inventory. We've seen an overall decline here on the right, for the last 20 plus years, a slow decline, but overall decline in the last decade. Enteric fermentation from livestock, energy and waste has come down, and including biomass burning, the low intensity, the managed prescribed burning. But then again, like if you look at 2019 to 2022, there were quite wet years. We had 3-year La Nina, so enteric fermentation, livestock grows very quickly. The number head, waste and rice cultivation went up again. Again, overall, there is an overall trend. It's important. But we do see quite a bit of variability, and what happens in terms of climate change and climate variability has also a large effect, even in the ones that we control ultimately, which is the direct emissions, anthropogenic emissions, including, livestock, the most important one. If we look at the changes in natural methane emissions, again, jumping from 2010 to 2019, we actually seen an increase. Well, we modeled an increase of wetland emissions, mostly due to the increase of overall temperature and also increased productivity of the wetlands, in part because elevated CO2. And of course, a big increase on wildfire emissions, methane emissions, because specifically on this particular decade, we had the 2019 big fires, particularly in the southeast of Australia. And we have now observational and modeling evidence that global wetland methane emissions are increasing. So this is a global application that we've done. It's not a specific one for Australia, but there's no reason why Australia should be any different from the rest of the world. And just to finish, here I'm going to show methane, CO2, and N2O. These are nitrous oxides. These are the 3 most important greenhouse gases, not the only ones. And I want to show you a little the relative importance, in this case, measured in a simple way with what we call the global warming potential. Global warming potential is not necessarily the ultimate temperature change put into the atmosphere, but it's largely driven by that. There's other factors that ultimately are important in that final temperature. And if we do what's called the global warming potential within a 100-year time frame, which is what the IPCC and the governments need to do as agreed in the Paris Agreement, you have that carbon dioxide, the single most important one by far, methane, and smaller N2O. Now, I said at the beginning that the most warming from methane comes from the first 20 years. And so if we were to then recalculate everything based on those 20 years, we have the methane in terms of the potential to warm the atmosphere. It is as important, if not even more important perhaps, than methane, than CO2. And of course, N2 are very small. Again, these are all this. It's neither the GWP 20 or GWP 100 are the perfect measure. And that's why we want to look at more than one measure to understand the relevance, short-term relevance, long-term relevance of anything we do, but nevertheless shows the tremendous influence that methane has in global warming. Just to say that we do have published. Actually, yesterday was published and now is accessible online, the actual research paper of the methane and nitrous oxide. So you can download it right there. Uh, these links will be made available, if not the whole PowerPoint. And then we have a fact sheet that I think that you may already seen, explaining very simply, the results. Thank you very much.
Thanks, Pep. Yeah, it's really easy to see the value of that work as Australia develops its pathway to meet emission reduction targets. So thank you. So I can see there's a number of questions already. Let's keep them coming. But for now, we're going to move on to our next speaker and we'll get to the questions at the end. So I'd like to warmly welcome Professor Peter Rayner. So Peter's research centres on estimating surface sources and sinks of CO2 using satellite and in situ data combined with models to analyse CO2 release and uptake patterns, particularly in the tropics and the Southern Hemisphere. He was awarded the Priestley Medal of the Australian Meteorological and Oceanographic Society in 2002, recognising his contributions to the field. Peter has held research positions at the National Centre for Atmospheric Research, NCAR, Princeton University, CSIRO, Monash University, and the Laboratory for the Science of Climate and the Environment in France. He currently leads a team of senior academics and developers on the development of the methane emissions model for open methane. So Peter, over to you, and your slides are ready to go.
All right, so I'm going to suggest we jump straight to the second slide. And let's describe first what open methane is. It's basically a platform and a tool. It's got a website where we try and publish the results and a bunch of stuff at the back end. One element of it is that we hope that every number and every line of code that we use is publicly available. So there's essentially nothing that we do that isn't open to critique and to comment. It's essentially going to use satellite observations to try and improve on the kind of information that Pep was describing in the first part of the talk. So we're going to use Pep's information and try and improve it. Let's go to the third slide. So basically there are two ways to estimate emissions of something, and Pep's described one of them in great detail. It's basically you put together as much information you've got on the ground, your understanding of processes from models, from inventories, however you want to do that, and you produce an inventory effectively of the contribution of different processes to the budget. The other way of doing it is to look in the atmosphere and say, if we measure an amount of stuff here, where's it coming from? So we can combine a whole range of measurements in the atmosphere, either from stations sitting on the ground, just measuring the areas it goes past, or planes flying around, or satellites flying overhead. And then we work backwards to say, well, here's the pattern of concentrations, here's a pattern of amounts of stuff we see in the atmosphere. Let's work back to see where it came from. And the analogy we always use is it's like tracing back the source of a bad smell to see where it's coming from. And we often distinguish these as top-down and bottom-up methods. The method I've just described is a top-down method. Next slide. So this method for methane in particular really came of age when we started to get decent measurement coverage. We've had a network of CO2 stations measuring around the world since the late 1950s, since people discovered that CO2 was actually rising in the atmosphere, but methane came along much later, and it's really the advent of satellites, satellite measurements that have really revolutionized the methane story. So we have a range of advantages to these satellites. They're totally independent of the kinds of techniques Pep was talking about. They've got a chance of getting a decent, broad national coverage. We might have a chance of seeing images of how methane is changing across the country day to day. So we've got a chance of producing a reasonably dense data set across the whole country, not just places we choose to measure. We can measure reasonably continuously. So if suddenly something happens that says there's a change of methane amount in the atmosphere, we can alert people to say, hey, look, it looks as though something's gone wrong here. And so that's something that we're working towards within the platform. It's also pretty scalable. So it turns out that flying a satellite is really expensive, but it does give you pretty much global coverage. And so the ability to suddenly decide, we need to learn what's happening in India or in South America or whatever from satellites is reasonably straightforward. If you're going to do this from the ground, it's quite hard. Now, the satellite we use is called the tropospheric, or the instrument's called the tropospheric monitoring instrument, TROPOMI. It's a remarkable instrument flown by the Europeans, and it's really the start of a long family of these measurements. So we're guaranteed a stream of these measurements into the future. It's been flying since really, I think it was launched late in 2017, but it's really been taking measurements since 2018. Next slide. So what can we do with these kind of measurements? Basically, we can produce a map of Australia's methane emissions. Now, the kinds of techniques that Pep was talking about, where you add up all the sources of stuff that's coming from the national inventory or from wetlands, some of these have a map attached. Some of them can tell you where they're coming from. A lot of them can't or don't. At least the data isn't published. So one of the things that we can do with a tool like Open Methane is to actually map where all the emissions are coming from. And we can also compare the expected emissions that we get from work like PEP's to what's actually measured in the atmosphere, and provide a cross-check that's totally independent of industry and government on what these numbers are doing. When a system's really rolling, we can produce pretty timely results, perhaps within a few days of the emissions actually happening. We can see how quickly things are changing. And as I've already said, it's actually surprisingly low cost. I mean, it looks incredibly expensive to the person flying the satellite. The data for us, by the way, is free. So the data source that we're using comes at absolutely no cost, thanks to the generosity of the European Union. Next slide, slide 6. So that's the good news. What's the bad news? Satellites can't see everywhere. They can't see through clouds. The satellites we've got currently can't see over water. They can't easily see through lots of smoke, so you can't actually look into the heart of a bushfire and see how the methane is changing. They have finite resolution. The satellites don't measure exactly what's happening at a point. They measure over a footprint that might be a few kilometers by a few kilometers, and they don't necessarily measure everywhere all the time. They're flying a particularly complicated pattern over the surface of the Earth, and they measure methane along that pattern. So it can be hard for us, for example, to say we saw some methane in the atmosphere, but did that come from cattle? Did it come from a mine? Did it come from a wetland? If those things are all happening together at the same place, it can be difficult to do. So if we have two sources that are happening in the same grid cell within our map, the same square within our map, it can be hard to pick. But nonetheless, it's still providing an unprecedented density of information. Slide 7. So the first thing we've done with Open Methane is to have a look in some detail at checking the large point sources, which are a really critical driver of methane, of where methane's coming from. So the way we think about this is we look for local enhancements. So that's places where methane is higher than the surrounding background, and it's higher than perhaps we think it should be. And so this is we've given a rough guide to how we do this. We use a combination of models and observations. So we use a model to say how much methane do we think should be in this region if the emissions are what PEP and the national inventory tells us they are. So we model the amount of methane very close to the emission, and then we model the amount of methane a bit further away from the emission. We can do that with a single experiment and say, so how much is the expected methane enhanced very close to our source? Then we can do exactly the same thing with the satellite. We can say, okay, so do the satellites see the same amount of enhancement relative to the background as the model? And if they do, it's fine. We say, well, as far as we can tell, there's agreement between what PEP or the national inventory thinks the source should be and what the satellite thinks it should be. If there's more methane in the observations than there is in the model, then we say, hang on, the model is probably underestimating how much is being emitted at this site. And so we can run this direct cross-check to see how the point sources compare with what we actually see on the ground. Now, it's important to know this is a not uncommon technique, but most people just use the observations. So it's pretty common to say, oh, we've seen more methane in this region than in surrounding regions, so there's a source. Not much value about that. We already know that there's going to be an extra source. The question is it bigger or smaller than we expect? Next slide. So here's the first set of results we've got on this. So what we've done is taken a bunch of large point source emissions, and we have compared the expected enhancements with the observed enhancements. And the couple of different lines that we see here is one of these is the emissions that we kind of predict from the national inventory. The other one is a line that's predicted by an independent data set called Climate Trace that actually thinks our coal mine emissions, for example, are much larger than the national inventory does. And we've also got the points that are actually observed by the satellites. Now, I'm not going to comment here on specific sites, but what we generally see is there's a significant underreporting from the national inventory and overreporting from Climate Trace. So this suggests that from these big point sources, the national inventory is probably underselling what the emissions really are, and this independent data set, Climate Trace, is probably overestimating what they are. We're showing a result here for a single month. It absolutely holds up for a much longer period. This is quite a general result. Next slide. So that's a simple cross-check, but what does it actually say about the emissions? So here we have an emissions map for the period we've just taken, January to July 2023. And what we've really highlighted here is essentially Australia's strongest point sources for emissions. And now all of these encompass coal or gas production effectively. And it's suggesting pretty much in line with the figures that we saw on the previous slide that fossil fuels might be contributing twice what we thought they were contributing. Now, that has interesting implications for what's the important low-hanging fruit for dealing with Australia's methane emissions, because if it's double, then the fossil fuel contribution is actually pretty comparable to the livestock, to the agricultural contribution, whereas we've normally thought that the agriculture was about double. So that's already an important policy implication if this turns out to be correct. As I said, it pretty much confirms these first set of results of significant underestimation. Next slide. So it's worth thinking about the consequences of this. If we're underestimating the fossil fuel emissions in general, it probably suggests that the methods that we rely on to calculate those emissions are wrong. So this was Pep's comment on perhaps we're casting some doubt on the actual methods that are used in the national inventory. Now, that's important because it tells us not only that our understanding of national emissions might be wrong, that the optimum pathway to reduce our emissions might be different than what we thought. We might need to concentrate a bit more on fossil fuel. It casts a little bit of doubt on the credibility of our attempt, say, to reduce methane emissions by 30% by 2030, as we've promised to do. Most importantly, I think, it casts doubt on the methods that we use to project the results of new mines or mine extensions into the future. That if these methods are wrong, then it suggests that the methods, which are exactly the same as the ones we use for the future, are probably going to substantially underestimate the impact of those future mines. Next slide. Just in summary, the satellites look like they're really pretty good for the big picture. But if we wanted to go beyond making comments on these general methods of underestimation and wanted to say what's happening in this mine or this mine or this mine, we really like to combine them with good local measurements. Now, the satellites are improving in that respect, but we can do a lot better. There are techniques we could be using now of putting instruments on the ground or on things like drones that could allow us to monitor facilities already. Australia has a terrible network for doing this stuff. The measurement infrastructure is really poor. We have about 2 sites, and in the area of Australia. Western Europe has about 70, and it's a smaller area. So you can see that we're relying on the satellites to a degree that we'd probably rather not do. So it limits our ability really to monitor these big facilities for compliance with things like the safeguard mechanism. And we could greatly improve that at a pretty modest cost. It probably costs a few $100,000 for around these billion-dollar facilities to do a much better job. Last slide. So what are we doing next? It's, as I said, the tool's completely public, and given the website that you can have a look at it. We're basically going to process historical data to go back as far as we can over the satellite period. There are older satellites that don't provide nearly so much data, astronomy, that we'll probably use as well. We'll also pick up as much as we can of the new data. So recently, the government's improved the way it reports on the safeguard mechanism, so we can see rather more than we used to of what's happening per facilities. And there's lots of satellites coming down the pipe that are going to greatly improve the precision and the resolution. So we can actually distinguish sites more clearly, and we can make much more confident statements on this kind of approximately double. And we're going to keep pushing to actually put a decent network of monitoring on the ground as well. I'll stop there.
Thanks, Peter. Yeah, that was really amazing to hear a bit about some of those technical aspects involved in developing a better understanding of like the hotspots for methane. Yeah, thank you very much. Okay, well, it's that time for the Q&A section of the webinar. If you have questions, as I mentioned, you can ask them of Pep and Peter through the Q&A function at the top. We're going to start with a few questions that were submitted before today, and then we're going to move on to some of the ones that we've received in the Q&A. So we'll work through as many as we can. Question number one, what is being done, and I think this has been covered, but there's a key element, what is being done about measuring fugitive emissions for a better understanding of carbon footprints and where to intervene for best effect?
Shall I perhaps respond to that, since it's pretty much a continuation
Extension.
of my last point? Yep. So I've commented on the improving tech and on what could be done with the network. There's one point I didn't mention, which is that the Australian government has a review on this very question, on how to build some of the techniques I've been talking about into improved monitoring of the safeguard mechanism that deals with large polluters. That's being run by the former chief scientist, Kathy Foley. It's going to report, I think, in early 2027, and Australia has a chance to really be a world leader in building these kinds of independent cross-checks into its regulations. So watch this space. There's a lot about to be happening. I wish it was happening sooner, but it is going to happen.
Fantastic. Thanks, Peter. Pep, did you want to add anything, or are you happy to move along?
Yeah.
Great. Okay, so I might move on to this one. So what proportion of emissions are from landfill versus wastewater and sewage treatment? And are all old landfill sites being monitored?
Yeah, okay, I'll take this one. So about 8-9% of all methane emissions come from waste, but about 90% of that come really from the landfills, what we call solid waste. The rest is everything that it's very aqueous, like water residues from both domestic and industry. So are they all monitored? Well, we have Peter will be monitoring all of them. That's number one. You can add after. But what we're doing is that we're not monitoring all of them. What happens is that in some of the bigger ones, we are actually doing things about it. We're doing capture, utilization. I'm happy to talk about more about this one. And then there's, of course, a very long queue of smaller landfills, which, nothing is done because it would just be too costly to begin with. The one good thing is that the distribution of emissions in landfills is that we have few very large landfills accounting for a very large fraction of the emissions. And then we have a long queue of smaller landfills that account for, smaller fractions, which basically means that landfills are a really good target, those which are not already targeted for mitigation, because they're very concentrated on the big ones, and we know what to do about it.
The only thing I'd add is there have always been concerns about old landfills. How long do they go on leaking? And at the moment, those leaks are too small, too weak for any individual landfill for the techniques I've been talking about to see them. But as the satellites improve and the monitoring improves, we've already seen that this can be done for larger landfills. As the tech improves, we'll be able to see into smaller and smaller and more diffuse landfills.
Great, thanks both. So on to the next question. Will biomethane or renewable methane be less susceptible to leakage than fossil methane? In other words, is the major concern in mining, or are transport and use also significant problems?
Okay, I can have a cat to begin with. So the quick answer would be that it will be less leaky, and just because we're comparing now, for instance, open mine coal, which there's very little we can do about it. These open mines, they leak a lot of methane that is there, and it's just difficult to do anything. The underground mines are easier because for safety reasons they need to be the air needs to be kind of move out, and methane needs to come out, and so then it's easy to do things with it, with that methane that comes out. So overall, we do see that factories or processing for biomethane would fall more into the kind of leaks that we see from the gas and oil industry, which are much smaller than the mining component of it all. So you would end up, having less. And that doesn't mean that we have to have leaks in the industry if we do biomethane. Leaks can be fixed. Sometimes leaks are issues that have been left unattended. So there's no reason why we cannot move into a much more tighter, methane type of industry if a renewable methane industry were to develop at the scale, of course, comparable to the scale we have now with coal and gas, which is humongous, and it's unlikely that we can actually go to those scales for biomethane, just because we don't have the type of biospheric organic materials to fit into it.
Yeah. Just want to add, there's a little bit of a bad news story here, in that one of the things we've noticed is that the likely sources from things like extraction of coal seam gas, so the leaks that we see around the places where the gas is actually being extracted from the ground, are larger than we think the inventory claims. And there's a previous work from people within CSIRO that suggests that's the case as well. But as well as that, there's also work from measurements around cities that is starting to suggest, and we haven't finalized these numbers yet, that emissions from leaks in the urban distribution might also be larger than we think. And we've seen cases in other cities where this happens. So yes, we think we'll do better with biomethane, but if we keep using gas, it's pretty likely that some of it's going to keep leaking.
Fantastic. Thanks, really great comprehensive answers. So yeah, moving along to the next question. And this one has come from the Q&A. Just wondering if the potential for increased occurrence of marine algal blooms, such as currently happening in SA, South Australia, might impact on future figures.
I would immediately say yes. We haven't studied this one, but the substrate always has to be organic matter in anaerobic conditions, and of course oceans, coastal zones. We've seen this thing in rivers as well, and lagoons. All the history, all throughout the history. It's just now it's happening a little more often. You would increase, no doubt about, the amount of methane that reaches the atmosphere. So yes.
Peter, did you want to add anything, or happy to move on?
Happy to move on.
Great. All right, it's a bit of a long question. I'll try and make this a bit easier. So, given that we want net zero carbon dioxide emissions and want to reduce methane emissions by about 30 to 60%, what is your view on landfill gas flaring that combusts CH4, so methane, to convert to carbon dioxide, CO2, and its contribution to net zero goals? For example, New South Wales EPA is championing landfill gas flaring as a way to drive state net zero goals. But from what has been discussed, I don't understand how that could be the case.
Yeah. Peter, should I go or?
Yeah, so you can probably comment on the overall.
Yeah, all right. So basically, flaring it's halfway through solving the problem, but it doesn't solve the problem. So basically, you capture a methane, which is as we said, it's super powerful warming with potential, and you oxidize it into you burn it, and CO2 comes out of it. And CO2, it has a less immediate warming, but of course, a fraction of it stays, for forever. So in the past, or in the 90s, when we started dealing with all this issue of the fugitive emissions, there was this huge push for flaring. That is, do not let methane go out, at least burn it on site, very easy, and at least you have CO2, which is less immediately powerful greenhouse gas. Now that's halfway through. You want to capture that methane and you want to utilize that methane. You want to take that methane and you can just put in an electricity generator and generate electricity. Put in the electricity for consumption locally, if it's an industry, or put it back into the grid for everyone to use and replace fossil fuel-based electricity. That's where we want to go. And that's what even actually some of the landfills we have already is exactly what we do. Just example of the one, I'm based in Canberra. We have a big landfill. We have more than one, but the bigger one, basically it has been working already with one major generator of electricity, and we're putting two extra generators. They put in a battery. It's like the whole thing is going to be this incredible system that can provide electricity, will eventually provide electricity for 10,000 homes in Canberra, all coming from the major landfill. So we can actually bring these things to more of the larger landfills, and of course, other industry that has these large emissions. And of course, coal mining, underground coal mining, is also one possibility. Usually there's flaring there, but there's also an opportunity for capturing that methane and utilizing that methane, and hopefully replacing, fossil fuel based alternative use.
Yep. The other thing I'd add is that there's recent research evidence that suggests that, at least for the places that they've looked at it, flaring is less efficient than we've assumed it was. So less of the methane's being converted to carbon dioxide than we thought. And so when we do these calculations of how efficient it is to flare and so convert powerful methane into less powerful CO2, we might be overestimating just how effective that is.
Yeah, thanks both. That's really interesting. So a question here for you, Pep. What methods were used to separate anthropogenic and natural fluxes for inland waters, such as rivers?
Very good one. And there's no method to do that. And it's so obvious that we have such a big problem. This can only be resolved with, of course, ultimately modeling with a lot of data that we don't have. And on this particular one, we had two choices: to say we just don't know, as it has been done in the past, to say that this is part of the natural fluxes, it's all in the rivers, or to do an informed expert decision. So we had a whole panel of people who contribute to a specific discussion about what do we know from any other research work done overseas or in Australia too, to decide and put a fraction to separate the anthropogenic to the natural background emissions. And so we came up with a number, was close to 50%, and that's what we applied. So again, the goal of our budget was to really bring all the fluxes, sources, and sinks, and be very clear and open about the uncertainty of those fluxes based on how well we knew them, how much data was informing the models we were using, or in this case, that was an expert opinion. So yeah, so it's a great question because it just shows that how much more we need to increase the observational measures that could eventually let us to be more honest as to how we do a partition, and therefore how human activities, direct human activities, are impacting methane emissions.
Great, thanks, Pep. So we're getting a little bit short on time, so I think we might make this the last question, but a nice practical one. Are there specific actions that local governments can take to address methane emissions in land use planning, waste facility management, sewage management, or other areas?
I can comment on a bit of that, and Pep can probably comment on some of it too. Do you want to go first, Pep?
No, you go.
Okay, so one of the things is whenever you're responsible for a piece of infrastructure, just make sure it's modernized. Now, it's easier said than done when there's money involved, and different parts of government, the government hierarchy in Australia, take responsibility for different things at different stages. But whenever you're looking at a landfill, if that's your responsibility, or whenever you've got control of some of the verification of the local gas distribution network or whatever, just make sure that it's being well maintained, because a lot of the inadvertent fluxes are coming just from poor maintenance. So that's, I think, a pretty low-hanging fruit.
And the other was what we're discussing about landfills. I mean, landfills are pretty straightforward. You don't reduce emissions 100%. There's a lot of diffuse emissions, a lot of things that you cannot capture, but the landfill mitigation was one of the first ones we had in the government. A methodology was developed a long time ago with some of the first mitigation projects that they were accepted under the Australian carbon credit mechanism, and so it has been working. It's just that even for instance, back to the case of Canberra that I know very well. There were not enough generators to take all the methane. So in this case, through the money that they get from the selling of the carbon credits, they have been able now eventually to extend to multiple generators, which will try to capture as much as possible. So and then at a smaller industry level, from the breweries, breweries have a huge amount of wet organic material left. There are opportunities to capture in digesters, tight digesters, the methane, and basically use it locally in the same brewery, either for electricity production or heat production. These are kind of, it's a very specific type of applications, which each industry will have a different best application. And if one can bring some of these ACCUs, meaning that the carbon credits, which, you make some money with it, I think that there are opportunities to support what, of course, will be an investment, to do that.
Yep.
Fantastic. Good one to end on. All right, so I'll make my wrap up pretty quick before we run out of time. Thanks to both of you for such fantastic and insightful presentations, and to all of you, the audience, for your active participation and engagement. Thank you for your support for the Climate Systems Hub. We really hope you've taken something away with you today, learnings, connections with others in this space, or just a wish to stay involved in the discussions around Australia's methane emissions. So on that note, we've developed a fact sheet summary of the methane budget work that Pep has done. He showed it before. We're going to put the link in the chat for you. And we'll also post a link in the chat to Pep's freshly published paper on this work. So we've got another great webinar lined up next month. Please subscribe to our newsletter so you can hear all about that. And then what else do we need to say? Just spread the word to anyone working in the climate science and adaptation space. Very last point, we love your feedback on these webinars. So there's just a short survey that's going to be popped in the chat as well. And then everyone who registered will receive an email with a link to the recording. So yeah, thanks again to our presenters and to all those who were active behind the scenes to get this off the ground today. See you next time, everyone.
Thanks again.
Thanks.
Thank you.